Our next application is going to be finding the area of a surface of revolution. This is slightly different from finding area under curve. Area under a curve is you're still in two dimension. Yeah, you're finding this area. Area of surface of revolution is, let's say I take this line and I rotate it and I get this 3D object and I'm finding the area of the surface area of that 3D object. So it's slightly different. We've seen how this 3D object can be formed by rotating a curve because we learned how to find volumes. Now, so the last application we are going to learn is to find the surface area of such objects. What is surface area? Let's say you have a cylinder, radius r, height h, and I cut it open here and I lay it out, it's going to look like a rectangle. This length here, that's the circumference, is going to be 2 pi r. And this length is h. What's the area of this rectangle? It's going to be 2 pi r h. In other words, the surface area tells you how much material you need in order to make that surface. When we say surface area, we don't mean total surface area. Total surface area is a different thing because, for example, for the cylinder, ideally, if it's used for some purpose, it's going to also have the top and the bottom, right? That would make the area more. So we just talk about one shape or just a basic shape like the cylinder, but it's hollow. And not just hollow, it doesn't have the endpoints. The surface area is 2 pi RH. Now what about a cone? We start with a cone and we cut it open. We're going to get something like this. This L is called the slant height of the cone. This bottom part is still 2 pi r if the radius is r. And let's say this angle is theta. Recall that in a circle, if you know the arc length, then this angle theta is defined as the ratio of the arc length over r. And the area of this sector, this is called a sector, is 1/2 r squared theta. So here area becomes 1/2, r is L here, L squared theta, 1/2 L squared. Theta is 2 pi r over L. L's cancel out and the area becomes pi r L. This is for the cone. Building intuition, for complicated shapes, we've seen our procedure is to find a basic shape that can be used for approximating. For volumes, we saw cylinders, cylindrical shells. For areas, we used rectangles. For arc length, we used straight line. Now let's see what would be helpful in this case. Let's say that's f of x, and that's a solid formed by rotating it. And let's take a slice. And this slice kind of looks like a bowl. Now it's a bowl with a curved edge. But then we use our trick from last time, which is the arc length trick, and we replace this curved line by straight edge. And we get the shape which is called the frustum of a cone, which is if you take a cone and you cut off the bottom part, what remains is this shape which is called the frustum of a cone. So this gives us the idea that our basic shape should be something like that. So let's find the area of this shape. Now, the frustum is characterized by two radiuses, the small one, the big one. Let's say I call the slant height of the frustum L, and then every frustum is associated with a cone that it has been cut out of, which is marked by the dotted line here. Let the part above the frustum be L1, and then the overall height be h. The area of the frustum is going to be the surface area of the big cone minus the surface area of the small cone, which is the dashed line. But we saw that the surface area of cones is pi r L. So this is pi r2 L1 plus L minus pi r1 L1, or pi r2 minus r1 L1 plus r2 L. Then you also have similar triangle. What is a similar triangle? Because it's 90 degrees and these angles are equal because the radius is parallel. That's R1, R2, that's L, that's L1. So L1 plus L2 for the big triangle divided by R2 is L1 over R1. If I cross multiply, I get L1 R2 is L1 R1 plus L R1. What does that give me? That gives me L1 R2 minus R1 is L LR1. I can sub that in here to get pi times LR1 plus LR2, and I do the averaging trick, multiply by 2 and divide by 2. I call this the average radius. So that is going to be the area of our frustum. Now for L, okay, I'm gonna now remember. Let's see. If you look at a shape that's been rotated, right? Let's say that's the shape. And then we look at this slice right here. This L is the arc length, right? Because that's that distance. Now we know that's what the arc length is. So in our formula, right here, L is replaced by this quantity that we are calling ds. What about these radiuses? Now that's the radius, right? The radius is just the value of f of x, which means it is y. So that's why your formula becomes 2 pi y ds, 2 pi x ds, where ds is secretly hiding this calculation for the arc length. Now if you rotate around the y-axis, things are slightly different. This is still the arc length, but now the radiuses are x, which is f of y. Yeah, that's why you have an x here. Maybe looking at an example might be helpful. Now this curve, y equals square root of 4 minus x squared between x negative 1 and 1, represents a arc of a circle. So that's what it is. 2, 0, negative 2, 0. But then we only want x to be from negative 1 to 1. So, oh, that erases everything. Negative 1 to 1 would be somewhere here, right? At 1, this is root 3, and at negative 1 is also root 3. Now this surface is rotated around the x-axis. So that's the shape you have. So about the x-axis is going to be 2 pi y, and I use the ds, and I'm going to use the one with y, right? Because I want dy. So this is going to be under root 1 plus dx over dy squared dy. So let's take the derivative. I get 2x plus 2y dy over dx is 0. Negative 2x over negative 2y is dy over dx. Or dx over dy is y over x. Alright, so I have 2 pi y 1 plus y squared over x squared dy. 2 pi y x squared plus y squared over x squared dy. But what's x squared plus y squared? It's 4, right? So this becomes 4y y over x dy. Now, what's y over x? We already see that that's actually dx over dy. So dx is actually y over x dy. So I can simplify this calculation, and this is just dx. And I know x varies from negative 1 to 1, so that gives me 8 pi. And that's going to be my area of the surface obtained by rotating this arc about the x-axis. So there's, of course, you can do it the long way. You can substitute, you can replace x in terms of y here, go through trigonometric integration, or use substitution and solve it. But you can also make some observations which makes your life easier. This one's rotated about the y-axis. So for y-axis, if you go up here, we're saying, where is it? We use the x form, right? So we have 2 pi x ds, but this ds is the square root of 1 plus dy over dx squared dx. So let's see. dy over dx is 2x. So I have 2 pi x square root of 1 plus 4x squared dx. Unfortunately, in this case, I'm not able to do any tricks, but the integration is not very difficult because I observed there's an x term outside, so I can use a u substitution equals du, which gives me x dx is 1/8 of du. So I have 2 pi root u du over 8, which is pi over 4 u to the 3 halves to third, whereas x goes from 1 to 2, so u is from 5 to, when x is 2, that's 4, 16, 17. 5 to 17. This cancels out, so the arc length is pi over 6, 17 3 halves minus 5 to the 3 halves. Sorry, not arc length, the surface area of the resulting surface. So that's it. That's the end of application of integration.